Okay, so in today's experiment, we're going to be looking at determining the limiting reagent, and we're going to do this with potassium oxalate and calcium chloride. And so, what we're going to determine from this reaction is which reagent is limiting, and we're also going to determine the percent composition of a reaction mixture because we're going to start with a mixture of calcium chloride and potassium oxalate. All right, so let's think about limiting reagent from a practical perspective. If you look at this vehicle, this car, right, you can quickly determine what's the limiting reagent if all the other parts are there, right? You see the two tires are missing, two of your wheels are missing, so your wheels are going to be your limiting reagent in this particular case, right? If you think about baking cookies, right? If this recipe makes 2 dozen cookies and I take away the butter, right, or cut the butter in half, the recipe here said that you can make 2 dozen, but if I cut the butter in half, then I'm not going to be able to make 2 dozen. I'll only be able to make 1 dozen because I only have half of the butter necessary to make 2 dozen, right? So hopefully that's starting to make some sense. So what is the limiting reagent? The limiting reagent is the reactant that governs any reaction. So when it's gone, the reaction is over, right? That's the main point that I want to drive home. When the limiting reagent is gone, the reaction is finished, right? Because the other reactant can't doesn't have anything to react with, right? It's also the reactant that's present in the lowest number of moles. Again, that makes sense, right? If there are less moles of it, when it reacts and is used up, then the other reagent, what we call an excess reagent, is still present and not used up. Because if everything is ideal, the number of moles of the limiting reagent, that's how much of the other reagent is going to react if they're in a 1-to-1 ratio. And then your other reactant is considered excess, right? So whatever doesn't get used up is considered the excess reagent, right? So in today's experiment, we're going to take calcium chloride dihydrate, react it with potassium oxalate hydrate, and in that reaction, we're going to generate calcium oxalate and then potassium chloride and water, right? But the calcium oxalate is insoluble in water, so when that reaction is happening, you're going to see the calcium oxalate start to precipitate, right? So we need to know the molecular weight of everything so that we get able to calculate the number of moles, and the molecular weight is simply the mass of all of your atoms together. We also need to know how to balance an equation, and that's important because when you're calculating the limiting reagent, you need the stoichiometric ratio of reagents, right? So the if you look at calcium chloride, there's a 1 understood to be there. Just like when you look on the other side of the arrow at KCl, there's a 2 in front of the KCl, right? So we need to know how to balance the equation so that we can have the proper stoichiometric ratios of reagents when we try to calculate the amount of one reagent relative to an unknown reagent or something that we don't know, right? We're able to quantify one in terms of the other. If I have the moles of potassium oxalate, I can use the stoichiometric ratio from the reaction to determine the number of moles of calcium chloride, and so on and so forth. Right? So there's a crucial step in the reaction, right? The reaction results in a precipitate. And so what happens is if I see the precipitate, and let's say that the precipitate is calcium oxalate, if I add more potassium oxalate, which I have here, if I add a little bit more potassium oxalate and I see more precipitate, what that tells me is that the potassium oxalate is limiting, because if the precipitation stops when potassium oxalate is used up, that means that it's limiting. And if I add more and I see more reactivity, that means that the potassium oxalate is limiting, right? So that's one of the parts of this experiment, or one of the aspects of this experiment that we're going to do. And then there's another crucial step, and we call it digestion. And what you do is you heat the precipitate uh, and redissolve it. And what that does is it ensures complete precipitation of all of your calcium oxalate. So we're going to warm this up. You'll see the precipitate start to kind of disappear or fade, right? It dissolves. You heat it for 15 minutes. And then when you stop heating it and you cool it down, you can see here that in the other flask over here on the right, the precipitate reforms when it cools down, right? So when the solution cools down, you reform the precipitate, and what that does is it forces all of the calcium oxalate to come out of solution and all of the limited reagent to react. What you don't want to do is heat it past 75, because if you do, then what happens is you drive off the water, and so your product becomes, your precipitate becomes the anhydrous salt rather than the hydrate. And that matters because when you're calculating percent yield and you're calculating limiting reagent and the theoretical yield and things like that, the hydrate is going to weigh more, 18 grams per mole more than the anhydrous salt. So you don't want to drive the water off. You want to retain the hydrate. All right, so here's a problem. We have a 1 gram sample of calcium chloride. It's straight from the lab manual, by the way. You react that with potassium oxalate, and you add it to water. You dissolve them both up, and after drying, the mass of the calcium oxalate recovered is 0.354 grams. When you add more potassium oxalate to the solution, right after you filter off the solid, a little bit of precipitate is formed. So that means that the potassium oxalate is limiting, right? In doing that. And so what we want to know is, what is the percent composition of the salt mixture, right? You started out with calcium chloride and potassium oxalate. And so we want to know the percent composition, which we can calculate using the mole to mole ratio and the amount of calcium oxalate that was generated. And we want to know how many grams of calcium chloride were in the salt mixture. So let's talk about that. So we have here, we find the number, first of all, find the number of moles of calcium oxalate that we generated as product, right? And we had that was given in the problem, 0.354 grams. Well, if we divide that by the molecular weight, grams over molar mass equals moles. We divide it by the molecular weight, we get the number of moles of calcium oxalate. And then using the stoichiometric ratios from the balanced chemical equation, right, we can take that number of moles of calcium oxalate and determine the number of moles of the limiting reactant, which is potassium oxalate, right? So if we take the moles of calcium oxalate and we multiply that by the mole to mole ratio with potassium oxalate in the top, so and calcium oxalate in the bottom, so we cancel those two out, then we're left with the same number, right? Because the mole to mole ratio is 1 to 1. So we have a 0.00242 moles of potassium oxalate. Once we know that, we can figure out how many grams of potassium oxalate we started with, right? We convert moles into grams. We take the mole value, multiply it by the molecular weight of potassium oxalate monohydrate, and we see that there are 0.446 grams of potassium oxalate, right? And then to know the percentage, we started with a gram. Part of that was 0.446 grams, and so we take that and divide by 1 gram times 100. That means that there was 44.6% of potassium oxalate in that starting mixture. And what that means is that there was 55.4% of calcium chloride in that starting mixture. All right, so once we go through tomorrow, right, the main thing I want you to know is that we're going to have to do that digestion step, and we're going to have to do a filtration. So I need you to read the lab manual, make sure you come prepared, bring your goggles, because we're going to be using hot plates, and you cannot work with any of this stuff without your safety equipment. All right, if you have any questions, you can email me. Thanks.